Good afternoon, everyone. I hope you're doing well. Today, we're going to continue our talk in kinetics about reaction mechanisms. And that's just a fancy way to say, how do reactants become products? And what are the steps involved? So the first term there, if we had an elementary step, that is a reaction happens in one step. Well, if that was always the case, we wouldn't have to study kinetics very much. We wouldn't have what's called a mechanism. So it just happens in one step. The molecularity of the equation is the number of species or the number of reactants that need to collide. So the number of reactants that are colliding is going to give us what is happening to produce this reaction. So the molecularity of it. So number of reactants to produce products. Okay, and then I think you can get from the stem of the words here that what they mean is unimolecular, bimolecular, and termolecular will be 1, 2, and 3. So a reaction mechanism is a series of elementary steps, so a series of equations that the sum has to equal the overall balanced equation that's given. And then again, we talked about that our rate law has to be done experimentally and see if it agrees. Now, our rate determining step, I want you to focus on that it has to be this slow step. If you think about, imagine using a funnel. If you're using a funnel to add liquid to a container, the liquid is only going to go into the container as fast or as wide as the opening of the funnel is. So the funnel is going to be the slow step, the size of the funnel. Do you have something with a really small opening or with a larger opening? Think about filling up your gas tank. You can only do it so fast. It doesn't matter if you push down on the handle harder, it's only going to allow a certain amount of gas to go through the hose that's going to go into your gas tank. So that is our rate determining step is based on our slow step. So if you turn the page here, you can see in this first thing that's found in your textbook that unimolecular, I have one little product right here. If I go over to my rate law and pay attention to the raised power there, that is also 1. Bimolecular is 2. If I look here, I have 2. Same thing here, I can add those up and I get a bimolecular equation. And so this is just showing you that the reactants could be the same as A and A or 2A, or they could be different. It doesn't matter. I also added 2 more terms here that aren't printed in your thing, so you might have to pause for a second. But a catalyst, so you can get them written down. A catalyst is a species present in a reactant, and in the reactant part of the equation appears as a product, but is not in the overall balanced equation. We know that catalysts speed up reactions. You guys have talked about that in the past. An intermediate species is a temporary product that's formed, then it's consumed, and it is not in the overall part of the balanced equation. Now, I know you guys have some more room to go ahead and write in this spot right here. So I'm going to get a new page, but I'd like you guys to write the equations that I'm going to show you these 2 terms through. So go ahead and continue to write there. So we are going to take equation 1, which is going to be nitrogen dioxide. I'm going to add it to another molecule of that. This is going to have a certain rate, and it's forming these products. Then I'm going to have experiment number 2, and I'm going to have nitrogen trioxide added to carbon monoxide. It's going to have its own rate, so we put that as K2, forming these products. Okay, another thing that you're going to see often is it's going to tell you which one is the slow step and which one is the fast step. So this is our slow mechanism. Most of the time, that's going to be the equation written right. So this is like our funnel if I use our example that I just mentioned. Okay, so in here, we can find that catalyst and we can find the intermediate species. So we said the catalyst is present in the reactant and as a product, but not in our balanced equation. So what we need to do is we need to add these together first and find our balanced equation. So let's find that. Okay, so in our balanced equation, if I jot down and use another color here, I can see that NO2 is present in both, and that's going to cancel out if I use like Hess's law on opposite sides of the equation. I can see the same thing here, that NO3 is on one side. I have 1 mole on the left, 1 mole on the right. That's going to cancel out. So everything else looks like it's a different species, so I can go ahead and add them up. And this is going to be my balanced equation with some rate going on, forming these products. Okay, so if I apply the definitions that we just said, we said a catalyst is present as a reactant, again as a product, but is not in my overall reaction. So that would be the one that I squared, put a square around. So that is going to be my catalyst, is going to be nitrogen dioxide was added to speed it up. Now, can a catalyst be present in the slow reactant? Yes, it can. It also can be in our overall rate law, even though it's a catalyst. And then we have an intermediate species. And our intermediate, if you look at the definition, it says that it is formed as a product, then used up as a reactant. So it's temporarily formed and then used up or consumed. So that in this case would be nitrogen trioxide. Okay, so I hope that makes some sense to you. I have a couple that I want you guys to try to do the same thing with. So in these proposed mechanisms, there is 3 examples for you. I want you for each one to find the overall balanced equation. I want you to find the catalyst, spell this right, and then I want you to find the intermediate. And then I also forgot something on the last one. I want you to find the molecularity of the equation. And that is going to come from your balanced equation, from the overall balanced equation. So if I go back up, let's see, I have it on the next page. If I go to here, my molecularity for this equation, I would look and I have 1 reactant, I have 2 reactants, so this would be a bimolecular equation. Okay? All right, so that's what I want you to do. I would like you to just look at the next 3 examples of the proposed mechanism. So we have one here, and then we have one here and here. And then we will talk about those answers in class. Have a wonderful day.